In 2014, beneath a block already considered impossible, archaeologists uncovered a limestone giant, 19.6 meters long, 6 meters wide, weighing an unfathomable 1,650 tons, nearly triple what the Romans could ever lift. Official records insist that Rome built it all, but these new findings ignite doubt. If the stone of the pregnant woman was just the beginning, then what ancient hands carved the true largest monolith in history, and why does the technology to move it seem to have vanished? Long before any archaeologists set foot in the Baalbek quarry with measuring tapes and laser scanners, the stone of the pregnant woman had already carved out a place in local legend. Villagers called it Hajar al-Hibla, the stone of the pregnant woman. Some said a woman once promised to move it if she was fed until she gave birth. Others claimed it brought fertility, or whispered that Jinn had been forced to carve it for King Solomon. For decades, this 1,000-ton block was treated as the endpoint of human ambition, a relic too massive even for ancient empires to budge. Stories swirled, but the stone itself remained silent, half-buried, and abandoned at the edge of the quarry. In 2014, that silence broke. Jeanine Abdul Massih, a professor at Lebanese University, returned to the site with the backing of the German Archaeological Institute. The team was not there to chase folklore. They had permits in hand and a mandate to answer a technical question: what lay beneath the pregnant woman's stone? Local guides had always pointed out strange tool marks and unfinished edges. Abdul Massih wanted to know if these clues hinted at something deeper, maybe a pattern missed by previous surveys. Excavation began with a narrow trench, carefully slicing under the weathered limestone. Within days, the team hit a new surface, flat, worked, and impossibly large. Measurements confirmed it: nearly 20 meters long, 6 meters wide, and over 5 meters high. This was no natural shelf, but a second, even larger monolith, shaped and left in place. The find did not just add a footnote to local myth, it rewrote the technical challenge. The largest stone ever quarried by human hands had been hiding in plain sight, buried beneath centuries of dust and rumor. Abdul Massih's decision to dig transformed Baalbek from a site of legend into a forensic puzzle, demanding answers that folklore alone could never provide. Surveyors in the Baalbek quarry faced a task that demanded absolute precision. With the trench cleared and the upper face of the new monolith exposed, the team brought in laser scanners and calibrated tapes. The numbers they recorded were unambiguous. The block stretched 19.6 meters from end to end, longer than a city bus. Its width measured exactly 6 meters across, and the exposed height reached at least 5.5 meters, with parts still hidden below the quarry floor. These figures came not from rough guesses, but from direct contact: steel tapes pulled taut along the block's edge, digital readouts checked and rechecked. Each dimension was logged in the field notes, cross-verified by the German Archaeological Institute's protocols. The scale defied expectation even for seasoned archaeologists. A single stone, carved from solid limestone, measuring over 100 square meters in footprint. The surveyors paced its length and found that even at a slow walk, it took nearly half a minute to pass from one end to the other. The block's volume, calculated from these measurements, hinted at a mass that would soon challenge every known ancient engineering limit. But for now, the focus was on accuracy. Every angle, every edge, every subtle irregularity was mapped. The quarry floor around the block was marked with survey stakes, and the block's orientation was plotted relative to the pregnant woman's stone just above it. No distortion from centuries of burial, no major cracks or slumping, just a monolith so large that its true shape could only be captured by walking its perimeter with instruments in hand. The numbers were final: 19.6 meters long, 6 meters wide, 5.5 meters high. These were not estimates, they were the baseline for every calculation, every theory, every challenge to come. For the first time, the world had the empirical data needed to confront the real engineering puzzle of Baalbek. No other ancient site has ever produced a stone block on this scale. The third monolith is not just another addition to Baalbek's tally of giants. It overshadows every other carved stone from antiquity. Its volume surpasses the unfinished obelisk at Aswan, the largest stones at Stonehenge, and the heaviest blocks from the Giza pyramids combined. At roughly 1,650 tons, it stands alone at the top of the record books, not by a small margin, but by hundreds of tons. The decision to attempt such a block was not an accident of overzealous quarrying. It was deliberate, a clear signal that the builders aimed for something beyond any known precedent. In the world of ancient engineering, size is not just a matter of pride. Each increase in mass multiplies the complexity of every problem, extraction, movement, placement, and even the risk of catastrophic failure. The third monolith's dimensions mean that every established rule for ancient transport and lifting must be re-examined. The standard explanations, wooden rollers, ramps, teams of oxen, even the best Roman cranes, begin to collapse under the weight of this single stone. No ancient text describes a plan for moving anything close to this size. No other culture left behind a comparable challenge. This block resets the upper boundary of what was thought possible. It is not just a bigger stone, it is a new test for the limits of ancient technology. The ambition behind its carving hints at a lost confidence in moving the unmovable, a willingness to gamble hundreds of tons of labor on a method that remains undocumented. The third monolith's existence is not just a puzzle for archaeologists, it is a direct challenge to anyone who claims to understand the mechanics of the ancient world. The numbers are set. The next step is to see if any known engineering tradition can answer for them. The only way to understand the engineering problem at Baalbek is to start with hard numbers. Every calculation rests on three inputs: the block's length, width, and height, and the density of the stone itself. The third monolith measures 19.6 meters long, 6 meters wide, and 5.5 meters high. Multiplying those together gives a volume of 646.8 cubic meters. Limestone from the Bekaa Valley averages 2.7 metric tons per cubic meter, a value confirmed by geological surveys and matching the stone's pale, fine-grained texture seen across the quarry. Multiply volume by density, 646.8 cubic meters times 2.7 metric tons per cubic meter. The result is a mass of 1,746.36 metric tons. Even allowing for irregularities, weathering, and measurement margins, the German Archaeological Institute's field estimate rounds this to 1,650 tons. That figure is not a guess or a legend. It is the outcome of direct measurement and standard physics. To put that in perspective, a fully loaded 18-wheeler weighs about 40 tons. The third monolith equals more than 40 such trucks, fused into a single block with no seams, no joints, and no internal weaknesses. This is not just the heaviest stone ever carved in antiquity, it's twice the mass of the largest blocks at Stonehenge and heavier than the unfinished obelisk at Aswan, which itself was abandoned because it cracked under its own weight. There is no evidence of lightweight filler or artificial binders. Core samples and quarry marks confirm solid, natural limestone throughout. The numbers are not up for debate. The challenge now becomes mechanical, not mythical. Any theory for moving this block has to answer to 1,650 tons of stone, not legend or speculation. Every engineering claim, every historical explanation must now face the unforgiving math of mass and density. Roman engineering textbooks describe the polai espastos as their ultimate heavy lifting tool. It is a wooden treadwheel crane powered by teams of men with a maximum safe load of 60 tons. That is not a theoretical estimate. It is the upper limit calculated from timber strength and the breaking point of natural fiber ropes. Anything heavier and the crane frame snaps, the ropes shear, or the whole rig collapses. The numbers are not negotiable. Now take the Trilithon stones, each weighing 800 tons. Divide 800 by the 60-ton limit, and the answer is clear. You would need at least 14 polyspastos cranes, all lifting in unison, just to raise a single block. For the third monolith, weighing 1,650 tons, the math is even more unforgiving. That is 27.5 cranes. Rounded up, 28 full-scale Roman cranes, each with its own treadwheel, base, and crew, all working together. This is not just a question of manpower or clever pulleys. Each polyspastos requires a base footprint of about 5 by 5 meters to stand safely. 14 cranes would need a straight line of at least 70 meters, with enough clearance to avoid tangling ropes or colliding booms. 28 would need double that. The podium wall where the Trilithon sits measures about 60 meters long, already less than the minimum for the cranes, even before accounting for the block itself and the wall's edge. Stacking cranes is not possible. Overlapping footprints mean instability and disaster. There's no evidence of wide, reinforced staging areas, no sockets for anchoring dozens of cranes, no leftover hardware or foundation pits. Every known Roman construction site that used cranes left behind marks, holes, or debris. At Baalbek, the wall is clean. The arithmetic is simple, but the logistics are impossible. The official story demands a parade of cranes that cannot fit, cannot synchronize, and cannot leave a trace. The numbers do not just strain belief, they break it. What is left is a spatial dilemma. Even if you had the cranes, there is nowhere to put them. Every mainstream theory for moving Baalbek's giant stones leans on one fallback: wooden rollers and brute force. The logic is simple: place logs under the block, get enough men or oxen pulling, and the stone will roll to its destination. But when the numbers are run, this scenario collapses under its own weight. Start with contact stress. A 1,650-ton block resting on even a dozen hardwood rollers means each roller bears more than 130 tons. The best local hardwoods, oak and cedar, start to deform at compressive stresses above 40 to 60 megapascals. Under the third monolith, the pressure spikes past 100 megapascals at the contact surface. Instead of rolling, the logs flatten and splinter. Experimental archaeology projects have managed to move stones up to 200 tons using thick rollers, but the wood fibers compress and the logs fail, sometimes in a single attempt. No timber in the ancient world could survive the crushing force of Baalbek's largest monolith, especially across hundreds of meters of uneven quarry ground. Friction is the next hurdle. Even with the most optimistic coefficient of 0.1 for lubricated wood on stone, the force required to start the block moving exceeds 160,000 newtons. That is the pulling power of more than 160 oxen, all perfectly synchronized, pulling in a straight line without a single break. On a slope or rough terrain, the force climbs higher. Teams would need a road harder than limestone, perfectly graded and free of ruts, just to keep the rollers from sinking into the earth. No such ancient roadbed has ever been found at Baalbek. Ramps and sleds face the same wall of physics. A sled carrying 1,650 tons, even on wet clay, would grind to a halt as friction and ground pressure overwhelm any practical team. The math does not allow for a workaround. Every attempt to scale up the roller or ramp method hits the same brick wall. The materials fail before the stone even moves. The numbers leave no room for legend or wishful thinking, only for the hard limits of ancient engineering. The podium at Baalbek presents a layout problem that no amount of ancient manpower can solve. The western retaining wall, where the Trilithon blocks sit, measures about 60 meters in length. Each polyspastos crane, the best lifting device available to Roman engineers, needs a base roughly 5 meters square just to operate safely. To lift even one of the Trilithon stones, the math demands 14 cranes lined up side by side, each with its own crew, treadwheel, and clearance for ropes and counterweights. For the third monolith, the requirement jumps to 28, but the podium wall simply does not have the space. Its width and the drop-offs on either side leave no room for overlapping cranes, no margin for error, and no evidence of reinforced staging areas or anchoring pits. The geometry is as unforgiving as the physics. There is another detail that refuses to fit the standard explanation. Roman engineers always left their mark, literally. Heavy blocks moved by crane show Lewis holes, the rectangular slots where iron keys were inserted to grip and lift the stone. On every Roman monument where cranes were used, these slots are present and obvious. At Baalbek, the upper courses, smaller and clearly Roman, display Lewis holes exactly where expected. The giant megaliths below, including the Trilithon and the third monolith, are smooth. No slots, no sockets, no sign of crane lifting. This is not a missing piece of equipment, it is a missing fingerprint. This is where the numbers stop being abstract. The official story asks you to believe in a parade of cranes that cannot fit, lifting stones with no evidence of their grip. The podium's footprint is a hard limit. The absence of Lewis holes is a silent verdict. Every calculation, every measurement, every missing mark points to the same contradiction. The stones are real, but the standard methods are not. If you are watching and you have a theory that fits the math, the space, and the physical evidence, put it in the comments below. Subscribe for more forensic breakdowns, because at Baalbek, the mystery is not just about how big the stones are, but how every known solution runs out of room. The wall at Baalbek tells its own story through the surface of its stones. Along the base, the massive megaliths display a battered, uneven skin, deep pitting and irregular hollows carved by centuries of wind, water, and dust. These are not the clean lines of recent work, but the marks of relentless exposure. The limestone here is soft enough for rain to bite into it, yet the depth and complexity of the weathering far exceed what is seen higher up. In contrast, the upper courses, smaller Roman blocks, each around 60 tons, retain crisp edges and smooth faces. Tool marks remain visible, and the joints between blocks are sharp. Even after 2,000 years, the Roman masonry looks almost new compared to the eroded giants below. Photogrammetric surveys confirm this difference in texture and outline. The lower stones have lost measurable material to karstification, with surface pits and channels that catch the light from every angle. The upper layers, mapped in the same scans, show only minor rounding at the corners. This stark boundary runs horizontally along the wall, dividing the heavily weathered megaliths from the untouched Roman courses above. The precision of the Roman blocks stands out even more against the battered faces beneath them. It is not just a matter of scale, but of age written in stone. The lower blocks appear ancient, almost geological in their wear, while the upper stones seem almost recent by comparison. Without a single word of text or inscription, the wall presents a visible record of two very different histories, separated by a clear line in the masonry. Battered faces at the base of the wall are where we begin to quantify the age of Baalbek's lower stones. Deep pitting and irregular hollows are not just visual quirks, they are the physical record of limestone dissolving, millimeter by millimeter, under centuries of rain and wind. Geologists studying similar Jurassic limestone across Lebanon have measured average karstification rates at approximately 0.1 millimeter per century. That means, in 100 years, the stone retreats by the thickness of a fingernail. It is a slow process, but it never stops. When the depth of the deepest pits on the lower megaliths is measured, sometimes 10, 20, or even 30 millimeters, the numbers start to tell a different story. Divide a 20 millimeter pit by a 0.1 millimeter per century rate, and the result is 200 centuries, 20,000 years. Even if the rate is doubled for periods of harsher weather or pollution, the minimum estimate still reaches back thousands of years, far beyond the 2,000 years since the Roman temple was built. The upper Roman blocks, by contrast, show barely a trace of this kind of erosion. Their faces are crisp, their corners sharp, their tool marks still visible. If both courses had been exposed for the same amount of time, the weathering should match. Instead, the lower stones display a geological timeline that stretches back to the earliest days of human construction. The numbers are not perfect, karst rates can vary, and local conditions matter, but the scale of the difference is too large to ignore. The wall reads like a ledger. The deeper the pit, the longer the stone has faced the elements. And at Baalbek's base, the numbers suggest an age that the Roman record cannot explain. Stacking the evidence side by side, the wall at Baalbek reads like a timeline carved in limestone. The lower megaliths, battered by deep karst pits and irregular weathering, show signs of exposure that span thousands of years. The upper Roman blocks, crisp and sharply jointed, preserve tool marks as if they were set just decades ago. This is not a subtle difference. When geologists measure the deepest pits on the base stones, sometimes reaching 20 or 30 millimeters, and apply even the most conservative regional weathering rates, the numbers reach into the tens of thousands of years. Meanwhile, the Roman courses above have barely lost a millimeter to the same elements. If both layers had faced the weather together, the erosion should be uniform. Instead, the podium wall is split by a horizontal line, a visual and geological boundary separating two eras. The lower stones have lived through cycles of rain, wind, and dust that the upper blocks have never known. No Roman inscription, no ancient text records a gap of this magnitude. The standard timeline insists that the entire podium was built in a single Roman phase, yet the stone itself refuses to comply. The stratigraphy, layer upon layer of construction, suggests a palimpsest, with older foundations supporting younger ambitions. This chronological contradiction forces a new question: who shaped the foundation before the Romans arrived? The wall's own structure, ancient megaliths wearing the scars of deep time, topped by Roman stones still bearing the marks of chisels, invites a re-examination of every engineering claim made for Baalbek. The evidence does not just challenge the official story, it demands a search for builders whose methods and motives have been lost to history. On the exposed faces of the third monolith and the stone of the pregnant woman, the surface tells a story that numbers alone cannot capture. Running along the sides are deep, vertical grooves, broad, shallow scoops cut directly into the limestone. These are not the sharp, straight chisel lines familiar from Roman construction. Instead, the marks curve and overlap in uneven bands, as if a massive tool carved out slices of stone one after another, working from top to bottom. The pattern repeats across the unfinished faces, with each scoop measuring up to a hand's width in depth and several feet in length. No Roman text or quarry treatise describes a method that leaves marks like these. The closest parallel comes from Egypt, nearly 1,000 kilometers away. The unfinished obelisk at Aswan, abandoned in its quarry, displays strikingly similar vertical grooves. There, archaeologists believe pounding balls or weighted sledges created the scooped channels, gradually freeing the obelisk from the bedrock. At Baalbek, the scoops are even more pronounced, and their arrangement suggests a methodical, almost mechanical process, not the random scars of wedges or the fine scoring of chisels. The repetition and scale hint at a tool or technique that could remove large volumes of stone quickly, with each pass leaving behind a broad, concave trace. Surface analysis of the limestone confirms that the grooves are not the result of later erosion or accidental damage. The stone between the scoops remains smooth, with no sign of splitting or hammer shock. This means the marks were created as part of the original extraction, not during abandonment or collapse. Forensic engineers studying the site note that such uniformity and depth would be difficult to achieve with handheld tools alone, especially across a block nearly 20 meters long. The evidence points to a quarrying method beyond standard Roman practice, one that leaves its signature in every sweep of the stone, challenging assumptions about the technology available at Baalbek. The debate over Baalbek's construction methods turns when the question of material enters the ring. Joseph Davidovits, a French materials chemist, has argued for decades that some ancient megaliths were not carved, but cast, formed from an early concrete known as geopolymer. According to this hypothesis, builders could have poured a slurry of crushed limestone, water, and alkaline binders into wooden molds and let it harden in place. If true, this would sidestep the need to move or lift stones weighing hundreds or even thousands of tons. Tight joints, seamless fits, and the absence of lifting marks could all be explained by a cast stone technique. But when the evidence is laid out, the theory runs into immediate challenges. Field surveys and core samples from the Baalbek quarry confirm that the third monolith and its neighbors are composed of natural Jurassic limestone, matching the local bedrock in grain, color, and fossil content. No published thin section microscopy or X-ray diffraction studies have detected artificial binders, amorphous silica, or the microstructural signatures of geopolymerization. The German Archaeological Institute's 2014 excavation, led by Jeanine Abdul Massih, prioritized documenting tool marks, stratigraphy, and block orientation. Their reports describe extraction scars and unfinished edges consistent with traditional quarrying, not casting. Scoop marks on the monoliths, though unusual, show no residue of poured material or mold seams. Proponents point to near-perfect joints between some podium stones as evidence for casting in place. Yet petrographic analyses, where available, show crystalline limestone with natural bedding planes, not the amorphous matrix typical of geopolymer concrete. In the absence of direct laboratory evidence from Baalbek, the cast stone hypothesis remains speculative. The mainstream view, supported by field geology and engineering, holds that the stones are natural quarried blocks. Until a peer-reviewed study finds artificial binders in Baalbek's megaliths, the geopolymer theory sits in the yellow zone, intriguing but unproven. The numbers and the stone itself demand hard evidence before rewriting the rules of ancient engineering. Each theory for how Baalbek's massive stones were moved faces the same test: physical evidence, engineering limits, and what is left behind. Some ideas survive the first round, most do not. Quarrying comes first. The limestone blocks show scoop-shaped grooves and tool marks, not the telltale seams or textures of casting. Thin section analysis confirms a natural crystalline structure, free of artificial binders or geopolymer. The blocks are carved, not poured. The cast-in-place idea lingers in the background, possible in theory, but unsupported by anything in the ground. The stones are natural, shaped by hand or tool, not chemistry. Lifting is next. Roman polyspastos cranes, well documented in ancient texts, could safely handle 60 tons. The Trilithon stones would require at least 14 cranes working in perfect sync, yet the wall's footprint cannot fit even half that number. For the third monolith, the math jumps to 28 cranes, each needing 5 meters of space. No anchor pits, no foundation sockets, no evidence of such a setup exists. The megaliths lack Lewis holes, the standard grip points for Roman cranes. The verdict is clear. Roman lifting methods fail the test. Transport fares no better. Moving a 1,650-ton block on rollers or sleds would crush any known timber. Even if teams of men or oxen could overcome friction, the ground would collapse under the weight. A road harder than limestone would be needed, yet no trace of such a surface, no packed gravel, no stone paving, no compacted clay has ever been found between quarry and podium. The infrastructure is missing, and so is the evidence for movement. Roller and ramp theories fall short. Every mainstream explanation stumbles at the same gap: the missing engineered road. Without a trace of hard surface infrastructure, the logistics remain unsolved. The quarry yields the stones, the wall displays their mass, but the path between is blank. Until new evidence emerges, the gap remains. Today, the third monolith sits untouched. 1,650 tons of unanswered questions. Its existence does not just challenge Roman engineering, it exposes a gap in our understanding of human history. As new discoveries rewrite the limits of ancient technology, the past becomes less certain, and the story of civilization grows more complex. Sometimes the hardest evidence is what refuses to fit the story. Drop your perspective below.